Present the conference. Hypothalamus Artificial Intelligence, HI, and Research Center for Advanced Decision Technologies, RCADT, a division of HI. Digital transformation powered by real-time autonomous and intelligent algorithms. Dual decomposition. Case, Troll West Oil Rim. This chapter introduces two large-scale optimization methodologies, Lagrangian relaxation and the Dantzig-Wolff decomposition principle, which are strongly related to the basic concept, relaxation of restrictions of the original problem to break it into two problems, one master and another slave. The slave generates information to send problem can be decomposing to facilitate the solution of the entire problem. The slave problem generates information to be sent to the master problem, and it may be decomposed in several subproblems to facilitate the resolution of the entire problem. Paragraph 3 of the chapter deals with this case. Real case, Troll West Oil Rim Operation Optimization. Case based on the paper. Real-time production optimization in upstream petroleum production, applied to the Troll West Oil Rim. That is the application of the concept studied to the problem of planning and scheduling operations in a maritime petroleum field on the continental shelf west of Norway. Additional bibliography. An offshore oil and gas producing group has many internal couplings, such as mass and pressure balances, and well routing. In addition, there are only a few common limitations, in this case the total production of gas and water. By relaxing these constraints, a decomposition strategy can result in a subproblem for each cluster I. Each subproblem can be assigned its own part of the objective function, based on a cluster, and a second mandate that considers common capacity constraints. The problem has a decentralized topology suitable for decomposition strategies. An oil and gas producing group has many internal couplings, such as mass and pressure balances, and well routing. In addition, there are only a few common limitations, in this case the total production of gas and water. By relaxing these constraints, a decomposition strategy results in a subproblem for each cluster. In Lagrange relaxation, LR, the basic idea is to attach Lagrange multipliers to the common constraints in the model and relax them in the objective function, whereas Dantzig-Wolff decomposition, DWD, handles the common constraints on a master problem. The structure of the two approaches is the same. The master problem includes the total flow variables, pressures, and local flows are part of the cluster subproblem. Decomposition involves a problem for each cluster that can be solved sequentially or in parallel. In their original form, subproblems correspond to MIMP problems that are converted to MILP by linearization of nonlinear functions. When applying DWD, or LR, the subproblems are the same. However, Lagrange multipliers can be updated in three different ways. DWD includes as new variables, column generation, the weights of the convex functions for the extreme points, and LR can be based on one of two methods, supergradients or cutting planes. Foss et al. Use LR based on supergradients, which can be interpreted as a math heuristic method. Gunnerud and his group of research in the Norwegian University of Science and Technology, NTNU, presents a model of the Troll West Oil Rim, a maritime petroleum field on the continental shelf west of Norway, with severe production optimization challenges due to rate-dependent gas coning wells and that the oil phase is sandwiched in between water and gas phases. A typical petroleum production system, like Troll West Oil Rim, has multiple independent reservoirs from which several wells feed into multiples manifold joined by pipelines. The manifolds belongs to clusters. The pipeline flows provide input to the processing facilities where fluids are conditioned for export. This is commonly called the real-time production optimization, RTPO, problem that it is in use in the upstream industry today. RTPO is associated to systems with a decentralized structure, meaning that common constraints are quite few. RTPO is usually treated in a quasi-dynamic way by reoptimizing a stationary optimization problem, typically once a day. The diagram presents the offshore field, which is composed of 8 clusters, each of which can operate independently of the others. However, the planning of the field must be integrated. This is due to the joining of all clusters through the production line. In addition, different well completions can result in additional decision variables such as the rate of gas injected for a gas lift well, a technology commonly used to increase well life as reservoir pressure decreases. Taken together, this means that there will be both continuous and discrete decision variables in a typical RTPO problem. The well and pipeline system are divided into clusters. There are two groups in one that covers variety 1 and 2, and the second includes variety 3. Therefore, a cluster may include one or more varieties. Well production functions are modeled by linearizing a nonlinear model using a linear function by parts. This converts an NLP problem into a MILP problem. To minimize error due to piecewise linearization, good accuracy and small intervals between interpolation coordinates are needed. This results in many variables and will therefore be computationally expensive. To handle this, it is possible to dynamically insert interpolation coordinates in areas close to the solution. Initially, the problem is solved only by containing a small set of interpolation coordinates. The solution is then located, and more interpolation coordinates are inserted into that area and optimized again. When acceptable accuracy is achieved, the problem converges, with the added advantage that error limits can be calculated in the solution of the optimization problem. Decomposition approaches to optimization problems are a mature field in operations research. Alternative decomposition approaches exist, and their applicability depends on the structure of the underlying problem. Two alternative and related strategies are studied: Lagrange decomposition, LR, and Dantzig-Wolff decomposition, DWD. Gunnerud et al. Used LR to decompose a RTPO problem into parts and offer a robust option for complex production systems. Both methodologies are suitable for problems with an angular block constraint structure, which is the case RTPO. The idea of using a decomposed model is to accelerate computational efficiency and improve the quality of the results, close the optimal gap. There are two aspects to consider when choosing which constraints to impose on the subproblem. It should be easy to solve, as it is reoptimized several times, and it should provide good quality limits for intermediate solutions. The RTPO problem has a decentralized topology suitable for decomposition strategies. An oil and gas producing cluster has many internal couplings, such as mass and pressure balances, and well routing. In addition, there are only a few common limitations, in this case the total production of gas and water. By relaxing these constraints, a decomposition strategy can give rise to a subproblem for each group I. Each subproblem can be assigned its own part of the target function if it is cluster-based additive, and if a second term considers common capacity constraints. When applying DWD or LR to the RTPO problem, the subproblems are the same. However, Lagrange multipliers can be updated in three different ways. DWD includes as new variables, column generation, the weights of the convex functions for the extreme points, and LR can be based on one of two methods, supergradients or cutting planes. Foss et al. Use supergradient-based LR, which can be interpreted as a heuristic method. The objective of the optimization problem is to maximize oil production while satisfy the typical system boundaries, upstream, underground hydrocarbon reservoir, and downstream, inlet separator on downstream processing equipment. Production is constrained by reservoir conditions such as coning effects and/or the production equipment like pipeline capacity or downstream water handling capacity. Constraints may move from one part of the system to another part over time, such as water production may be low early on and increase dramatically during the decline phase of a reservoir, thereby making water handling capacity an issue. The downstream boundary is typically a constant pressure on the inlet separator. The decisions variables are production valve on each well, gas injection valves, and routing of the reservoir fluid. These are binary variables that convert the problem in mixed nonlinear programming, MILP. In the reference chapter, you will find the complete formulation of the case, Troll West Oil Rim. In LR, the basic idea is to attach Lagrange multipliers to the common constraints in the model and relax them in the objective function, whereas DWD handles the common constraints on a master problem. The structure of the two approaches is the same. The master problem includes the total flow variables, pressures, and local flows are part of the cluster's subproblem. Decomposition involves a problem for each cluster that can be solved sequentially or in parallel. In their original form, subproblems correspond to MILP problems that are converted to MILP by linearization of nonlinear functions. Discrete variables are related to the routing of materials through pipes. The diagram presents one of the 8 groups of trolls. In this case, the limitations of gas and water handling capacity are relaxed. By including all other constraints in the MILP model, this will represent the Lagrangian upper bound problem for the RTPO. If pi gas and pi water are the Lagrange multipliers associated with gas and water handling capacity constraints, the target Lagrangian function for the RTPO is presented below. The objective function, together with the MILP constraints, define the upper Lagrangian bound problem, LUBP. By relaxing these constraints, the problem can be separated into a subproblem for each group. To formulate the subproblem of each cluster I, the target function must be subject to local constraints. There are several alternatives in the literature. Foss et al. Selected a heuristic based on the subgradient described in Beasley that has been implemented. The procedure is iterative and systematically generates multipliers from an initial set of multipliers. The upper and lower limits of the solution must be calculated after each iteration. These limits can also be used to quantify the quality of the solutions obtained. The upper limit will be equal to zub, while the lower limit is usually found by some heuristics. In this case, this limit is only updated when the sum of the gas and water production of all the subproblems is less than the handling capacities. Then it can be defined that it is equal to the original objective function. The summary of the Lagrangian decomposition algorithm is: select an initial set of Lagrange multipliers. Initialize ZLB equal to 0 and set step size to 2. Solve the subproblems using Lagrange multipliers and get an upper limit sub, the sum of all the objective functions of the subproblems. If the solution is also feasible with respect to the original problem, update the ZLB. Calculate the subgradients for relaxed constraints. Check for convergence. The procedure may end after a certain number of iterations or when the gap is below some percentage. Define a step size that depends on the ZLB gap and the user-defined step size parameter. Update the estimate of Lagrange multipliers using the rule and then go to step 2. LR and the subgradient method is developed for LP problems. Since the subproblems are MILP, the method will not necessarily converge to a 0% gap due to the integer variables, as would be the case with LP problems. The reason is that marginal changes in Lagrange multipliers can lead to different integer values and thus to changes in the target functions of the subproblems. Gunnerud and his team start by assuming linear constraints and continuous variables, i.e., an LP problem rather than a MIL problem. Then the master problem is a reformulation of the integrated problem, CRTPO. Each feasible base point for each cluster is represented as a variable in the master problem and represents a production configuration specific to this cluster. The number of feasible basis points for any practical problem can be clearly prohibitive, and only a small number of these feasible basis points will be basic in the master problem. Then the idea is to constrain CRTPO by reducing the number of feasible basis points. DWD starts with some feasible basic points and checks whether the solution of the built-in problem is within a convex combination of these points. If this is not the case, new feasible basic points are included in a structured manner until the optimal solution has been found. When applying DWD to the RTPO problem, the subproblems will be identical to LR if the same common constraints are subject to relaxation. However, while Lagrange multipliers are updated using a subgradient heuristic in the case of LR, the update in DWD is done by solving a master problem of LP. Dantzig-Wolff decomposition. Master problem. Using feasible solutions of all cluster subproblems, the master problem, CRTPO, can be formulated as a convex combination of the extreme feasible points using the multipliers. The algebraic formulation of the CRTPO master problem is formula 87. The CRTPO problem produces the value of the Lagrange multipliers of the gas and water processing capacity constraints, which define the target functions of the subproblems. Dantzig-Wolff decomposition algorithm. Choose two feasible initial base points for each optimization problem in a cluster. One of these points can be obtained by assuming dual variables for global constraints equal to 0. The other point can be obtained by assuming another value for the dual variables close to zero, since the important thing is to obtain two feasible points for each of the subproblems of the cluster, which may be close to the optimal solution. Specify the master problem for the given set of feasible basis points, then solve it and calculate the values of the Lagrange multipliers for the global constraints. Solve optimization problems for each cluster using the Lagrange multipliers obtained in step 2 as the objective function. If the solutions to all the local optimization problems have not changed, the optimal solution has been found, and the algorithm ends. For any problem, the solution of which lies outside the convex set defined by the feasible basic points used in 2, add the actionable basic points to the master problem and go to 2. Therefore, RTPO is resolved, including also these new feasible base points generated in 3. 4 experiments were performed for each methodology. The difference between the cases is the difference in the number of clusters, 2, C2, 4, C4, 6, C6, and 8, C8, in Troll C. The gas capacity for each case increases with the number of groups. The fact is that the decomposition strategies, DWD and LR, are faster in all cases than the global method, full space, F, S, except in the smallest case, C2. F, S, does not converge to its termination criteria after 12 hours for the case of 8 clusters and typically has difficulty resolving issues that consist of 6 clusters or more. F, S, stopped after 12 hours, with just over 7.5% in the duality gap. DWD and LR end all problems with a duality gap of less than 0.5%. DWD shows superior performance to LR in terms of efficiency and robustness. However, LR's performance is superior to F, S, S, demonstrating that as problems grow in complexity, so does the advantage in favor of large-scale methodologies. 4 experiments were performed for each methodology. The difference between the cases is the difference in the number of clusters, 2, C2, 4, C4, 6, C6, and 8, C8, in Troll C. The gas capacity for each case increases with the number of groups. The fact is that the decomposition strategies, DWD and LR, are faster in all cases than the global method, full space, F, S, except in the smallest case, C2. F, S, does not converge to its termination criteria after 12 hours for the case of 8 clusters and typically has difficulty resolving issues that consist of 6 clusters or more. F, S, stopped after 12 hours, with just over 7.5% in the duality gap. DWD and LR end all problems with a duality gap of less than 0.5%. DWD shows superior performance to LR in terms of efficiency and robustness. However, LR's performance is superior to F, S, S, demonstrating that as problems grow in complexity, so does the advantage in favor of large-scale methodologies. The results show that parallel methods are significantly faster than monolithic or sequential methods. For large applied problems, there is no valid reason not to use a partition and decomposition technique. In this case, DWD is more effective than LR. Algebra is the intellectual instrument which has been created for rendering clear the quantitative aspects of the world.